Okay, yeah, thanks for the introduction, Clemens, and particularly also a big thank you to all organizers and potentially also reviewers if they're here in the audience for giving us this opportunity of having this talk here today. So as Clement already mentioned, so I will present both of the talks that have been intended for the MDH session, and since both talks are highly correlated with each other, I've just prepared one self-contained set of slides, which makes things, I think, a little bit more fluent and compact here. And actually, the second talk was intended to be presented by my colleague Richard. He's today also here. So Richard is responsible for a lot of technical things that I will present in the talk. And if there are any questions, he will surely be able to answer that. And yeah, I also might need to mention, so I will be mostly presenting existing work and also work in progress results. So that's not original work that we are presenting here. But particularly regarding the work in progress results, every kind of remarks, questions, even if they're mean, so they are highly appreciated. So we had also a talk, I think it was 2 years ago at the ARRAY workshop, where we had some lively discussion that really helped us a lot to shape our way in this direction here. So please feel free to ask any kind of question. And I can also, of course, take questions in between, so they don't need to be at the end. And I think this entire talk will be like 40-45 minutes at most, so that we should have plenty of time for questions at the end. Okay, but now let's start. Yeah, maybe just one quick slide so that you know who we actually are. So Richard and me, and also the two Hunlo brothers that you can see here in the bottom, we are a group, and we are working on the MDH, ATF, and HCA project. And these are approaches toward generating, optimizing, and executing code for data parallel computations, such as, for example, linear algebra routines, stencil computations, and all these kind of deep learning operators that we are seeing nowadays a lot. And these computations in the context of contemporary parallel architectures, such as, for example, GPUs, CPUs, and so on and so forth. And yeah, the two Hunlo brothers are mainly involved with a lot of implementation, so they can be considered as kind of software engineers in our project. So they are doing a lot of things regarding MLR. So they mainly try to bring the concept that we develop into the MLR project. That's what these two guys are mainly doing. Richard can be considered as the main technical engineer in our project. So everything that's related to implementation that you will see in the following, that's apart from the MLR stuff, is all done by this guy alone. So he's really doing a great job here. And yeah, I am something like a project coordinator or leader. So I started this whole thing, and I'm responsible more for the higher level concept, having the big picture in mind, giving these kind of talks, writing the papers, and these kind of things. So yeah, now I hope you have a rough overview of who we are and what we are doing. And okay, and the focus today will be mainly on our research on MDH, so our research on how we generate code and code generation stuff. I have like 2 or 3 slides about our ATF approach, which is about code optimization, so that you have at least seen it once, because ATF is not specifically tied or bound to MDH, so it's a kind of an optimization engine that can be used for any kind of project, so potentially also for your project. That's why I wanted to just present you what's ADF about and how it's used kind of quickly and roughly. And actually don't have slides about HCA. So HCA is our research on code execution. So that's mainly about host code optimization. So CUDA host code, OpenCL host code, high-level abstractions for programming these kind of host codes, how to easily express optimizations. I think it's also an interesting project, but for time reasons I had to skip the HCA project out of the slides here. So the goal of MDH and ATF. So MDH and ATF approaches to generating and optimizing code for data parallel computations. And if you just want to summarize kind of quickly in simple questions what these projects are about, the questions would be regarding MDH, so our code generation, our research on code generation. How can we generate code that can be fully automatically optimized for a particular target architecture and also characteristics of the input and output data, so such as, for example, the data size or memory layouts. And our research on ATF, so the second part of our research immediately follows up on this question, and it's now about the question, okay, we have generated code that can be fully automatically optimized according to MDH. How can we now eventually optimize it? So ATF is mainly about techniques from automatic program optimization, numerical search techniques, how can we represent search spaces so that they don't, efficient representation for search spaces, how can we explore these spaces, why the MDH part of our research is more about programming languages stuff, so formal semantics, domain-specific languages, search space specification, so how it's a search space needs to look like rather than how it is expressed, which is part of ATF. So that's how you can think about these two projects here. And yeah, the ultimate goal of MDH and ATF, and actually also HCA, which is not on the slide yet, but is to simultaneously achieve performance, portability, and productivity. And by performance, we really mean we try to achieve performance with this approach that is competitive to end optimized solutions. So like, for example, NVIDIA Q+ and QDNN, Intel 1MKL, 1DNN. So we don't try to have some kind of trade-off between performance and productivity or these kind of things. By portability, we mean both functional portability, but also performance portability. So with a program expressed in our approach, so with the same program code, we really try to achieve a consistent high level of performance over different kinds of architectures and also data characteristics. And productivity here means we want to free the user of our approach from any kind of hardware and optimization details. So that, for example, an AI scientist, a chemist, a physicist can completely be focused on its particular domain. Okay, now regarding MDH. So we have a website about MDH, so if this can somehow gain your interest, please feel free to check out the webpage about MDH, where we have a lot of examples, some illustrations, also some linking to code example and these kind of things. And if you prefer reading a paper, we have a bunch of paper about MDH, but I think the top last paper from last year that actually was also presented at PLDI last year, we consider this one as the main MDH paper here. So the goal of MDH. So first of all, MDH is a formal framework for expressing and optimizing data pair computations. And for this, MDH makes three major contributions, which are: MDH introduces a high-level program representation. And first of all, as part of this representation, we have tried to come up with a formal notion of data parallelism. So for example, data parallelism, I usually was struggling with this term because we have an informal definition, like applying a function independently to data. Then we have a lot of examples where we say they are considered as data parallel, like matrix multiplications, convolutions, but there was never really a formal definition. So the first thing that we tried is to really clarify what we understand as data parallelism in a formal way here. And maybe more interesting for today, based on the common algebraic properties of these computations, we have defined higher order functions for conveniently and uniformly expressing these kind of computations, fully agnostic of hardware and optimization details, while we still capture in the representation all the information that are relevant for eventually generating high-performing code. For example, in CUDA for GPUs or OpenMP for CPUs, and so on and so forth. So the second major contribution of the MDH approach is the low-level program representation. And in this representation now we really try to explicitly express and reason about optimizations for the memory and core hierarchies of modern parallel architectures like GPUs and CPUs. And we also try to generalize these optimizations that they apply to arbitrary combinations of a data pair computation in a parallel architecture here. And yeah, the last contribution of MDH is kind of a natural success of the two first contributions. The third contribution is a structured optimization process that fully automatically lowers an instance in our high-level representation to a device and data optimized instance in our low-level representation, based on auto-tuning actually, and that's, for example, where our auto-tuning ATF will come in the game, as you will also see later throughout this talk here. And yeah, again, so the focus today will be mostly about on the high-level representation of MDH, so mainly how MDH is used. I have like one slide about the low-level representation and one slide about the lowering process, so that you have at least seen it once, but the major focus will be on the high-level representation, so how MDH is actually used from the user perspective here. So MDH high-level representation. So while we have designed our high-level representation, we had three major goals in mind, which are, it should be uniform, minimalistic, and structured. And by uniform, we mean it should be able to express any kind of data pair computation without relying on domain-specific building blocks. So we don't want to have building blocks, for example, in our language design, mostly focused on linear algebra routines, and some building blocks mostly motivated by, for example, stencil computations. And if someone comes up with a different flavor, I say, of data pair computation, then we need to extend our language design, incorporate it into our optimization system. So we want to avoid these kind of issues completely by scratch from design here. Minimalistic means we want to rely on as less building blocks in our language as possible to keep the language simple. Simple for the user, of course, that uses our system, but also for us developers that need to eventually generate code from these blocks here. And structured means we want to avoid composition and nesting of these building blocks as much as possible for expressing computations, thereby again further contributing to the usability and simplicity of our language design here. Again, for the user, but also for us developers. So now we could show, that's also discussed in detail in the paper, that we only require three higher order functions to uniformly express any kind of data pair computation. And these higher order functions, you can see it on the top, it's a simple overview here. These are inView, MDHom, and OutView. And InView is always responsible for the input data. So there we specify the data accesses, and they mainly transform the domain-specific data representation, like for example scalars, matrices, vectors, and so on and so forth, to an internal data representation. MDOM is always responsible for expressing the data per computation, and AltView brings the internal data representation back to the domain-specific representation here. Okay, how does it look like for a very simple but I think still illustrative example like matrix vector multiplication? So on the top of the slide you can see how matrix vector multiplication is expressed in the MDH formal high-level program representation here. On the right side you have a straightforward C program that's completely equivalent to the expression that you can see here on the top. Parts that corresponds to each other are highlighted in the same color. And yeah, what's happening here? So InView captures the access to the input data. So in this example, we say, okay, we have a matrix M, we have a vector V, and at each point of the iteration space, we access a matrix at position ik and the vector at position k. MDOM now expresses the data per computation part, which is applying multiplication to the accessed matrix and vector elements. And then it says, okay, results, so the obtained intermediate results are combined in the second dimension, so the so-called k dimension of matrix vector multiplication via pointwise addition, so that's denoted as a plus symbol here. And we combine the results in the first dimension, so this so-called I dimension of matrix vector multiplication using concatenation, which is denoted as a double plus here in our formalism. And yeah, the output is actually instantiated trivially in this example, but it can be used in, for example, more advanced. Yes, please, Clement?
I already have a question.
Okay.
If you look at the V colon IK, does it mean, how does it, should I interpret this? You said this is the access pattern to the vector. It looks like a two-dimensional access pattern.
You mean
the right-hand side of the top box.
This one?
Can you repeat the question? Is this for the recording?
Oh, sorry.
Yeah, you can use your microphone as well.
Yeah, okay, I can repeat the question. My question was about the bottom right part of the upper box with the access pattern to V, which I would interpret as a two-dimensional access pattern to a one-dimensional data structure.
That actually maps the iteration space to the majority of the data. So here we say, okay, ik are indices of the iteration space, and then we map them to the k. So these I and k, you can consider them as this I and k, and this k here is this k. That's how the relation is between, or how these index functions can be interpreted. Any further questions so far? Okay. And I think I stopped by the output. So the output view in this example, so the output view is trivial in this example, but for example in matrix multiplication, the output view can be used to solve the result matrix as transposed or the like in a very structured way. And yeah, maybe as an interesting side note, we could even show that due to the minimalistic and structured design of our language, so we can even generate these kind of expression, as we can see here on the top, even from straightforward sequential code, so for example in Python or C. So we can just take as input the program that you can see on the right side with a simple annotation, and we can generate exactly the same program as you can see here on the top. And also, of course, for more advanced examples than just a matrix vector multiplication. And yeah, so in the paper we could show that we are capable of expressing various kinds of data per computation that actually differ in significant characteristics here. So for example, we could show that we can express linear algebra routines like dot products, matrix vector multiplication, matrix multiplication on transposed matrices, batch matrix multiplication. And actually we could even show that these expressions for linear algebra routines are evolve very naturally from each other, which is kind of intended because, for example, a matrix vector multiplication can be considered as multiple times computing dot. A matrix multiplication is like computing multiple times matrix vector multiplication, and that's exactly reflected even in our formalism or in our formal representation here. Then you've also expressed a further example, like for example convolution stencil, convolution-like stencil, Jacobi stencils, which differ from linear algebra routines by accessing neighboring elements in their input data. Then we have quantum chemistry computations, probabilistic record linkage, which is an important example from data mining and used to identify duplicate entries in a database, histogram computation, map-reduce pattern, prefix sum computation, and so on and so forth. So we consider this as a diverse set of different data per computations here. And yeah, what might be interesting, so kind of quickly and short to the point, so what's the difference between MDH and other kind of representation? So just regarding MDH high-level representation without the low-level representation and the lowering. So another representation that's kind of popular and very heavily used is a linear representation of the MLR framework here. And for example, compared to MDH, the two major differences that we see is so first of all, MDH explicitly captures the operators for combining intermediate results. So for example, in the case of matrix vector multiplication, we have seen that we explicitly express the pointwise computation, so this plus that's highlighted in red here, but we know what's the operator to combine different intermediate results in this dimension here. Compared, for example, to the linear program, it just says it's a reduction computation, but reduction can mean anything. So we don't have access to the operator, and so there's less semantic information captured in this representation, which complicates generating efficient code. So for example, if you want to also optimize and parallelize reduction-based computations within the actual targeted computation here. And a further interesting or important point is that MDH clearly separates the scalar operations from the operations for combining intermediate results. So in our representation, we separate the multiplication, so the so-called scale operation in MDH, from the addition and the concatenation. While in the linear representation, they are kind of fused together in the body of the linear generic. So this body of the linear generic can be kind of considered as a loop body here. And of course, for simple matrix vector multiplication, you might be able to make a semantic analysis of the body and extract these operators. But for already slightly more complex use cases, that might become much more complicated, and in the general case it's even impossible according to the Rice's theorem here. And yeah, we can exploit this additional semantic information in the MDH representation to achieve higher performance, for example, by also parallelizing and optimizing reduction-based computations, and it also contributes to higher expressivity, because for example, in MDH you can use different kinds of combine operators. So for example, a pointwise with a prefix sum that's, for example, required to express maximum bottom box sum. The maximum bottom box sum example, that's also kind of an important example here, which is not possible, for example, in algebra. And yeah, if that somehow could gain your interest, or if you're working with the linear dialect and want to have a little bit more information about that, so we had a presentation last year at the Euro LVM, and the slides are actually linked here. I don't know if these slides go online, but if so, you can easily find them. And maybe also maybe kind of quickly a comparison of MDH with TVM, which also kind of, or maybe this state-of-the-art approach for generating efficient program code from these kind of high-level abstraction for array computations here. So compared to TVM, the major strengths of MDH is again mostly regarding the combine operators here. So MDH allows using different combine operators, and we have a formally defined semantics for them. And we also allow, so using different kinds of combine operators, and we also allow to use arbitrary kinds of combine operators. For example, TVM is limited to a set of predefined operators here, while MDH actually allows you to define any arbitrary combine operator that just satisfies some type properties here. And actually this might seem to be like a slight difference or a simple difference here, but it's actually kind of challenging to have a formal semantics for these different kind of combine operators here. So that was also confirmed in the TVM community, and I also just can confirm it. So it was really a lot of trouble to come up with a semantics that makes kind of sense for these operators here. Okay, so far we have just seen MDH's formal program representation here, so just from a formal perspective here. But Richard put a lot of effort over the last months and years in providing a full implementation of the MDH approach. And he is working on a Python-based compiler here. And here on the right side in the red highlighted box, you can see how matrix vector multiplication would actually be expressed in our Python-based user interface here. And the interface is actually designed to be very similar to the formal representation of MDH, so that any kind of formal reasoning that we have for our formal high-level representation here also applies to our DSL programs. And here we can see, for example, we also have these three higher-order functions kind of expressed in Python: out view, MDHOM, input view. Index functions are expressed, for example, via Python lambda functions. Then we have this multiplication here, just expressed as a mul instead of the symbol, instead of the star symbol. We have CC for concatenation, PW for pointwise computation, the scalar plus, and so on and so forth. And also the type parameter. So I think that's a very close interface. So it's very close to the formal representation of MDH here, which we consider as good. And yeah, the slide before I mentioned that multiplication function, so that's actually a pre-implemented function by us, because multiplication is occurring for expressing many kinds of data per computations, particularly linear algebra routines and computations that are relevant for deep learning here. But we allow the user to use fully custom combined scalar functions here. So actually, I would say they're kind of easy to implement. You just implement them in Python, maybe a little bit different because the input types are a little bit different. But here you can see, for example, how the multiplication would be explicitly implemented in Python. You just use the function and annotate it with a decorator here, and that's everything actually you need to do to have a custom scalar function here. And for a pointwise operator, we actually also allow using arbitrary kinds of binary operators here. So in the matrix vector multiplication example, we have used the scalar plus so to express the pointwise addition here. But that can be also, again, any kind of arbitrary user-defined function here. We just implement it in Python, use a decorator, and if all type properties are satisfied, that's completely fine then. And we actually allow even fully custom combined operators here, so even different from concatenation and pointwise. So these two can already express a bunch of different examples here. But if you want to have a new kind of combined operator here, so for example, for prefix sum or something like this, it's actually also pre-implemented but different from concatenation and pointwise. But if you have something like this and that's not provided by us, you can also implement your own combined operator here. That might be a little bit more challenging. I would say if you get a little bit familiar with it, it's kind of okay, but it's a little bit more challenging than just implementing a scalar function or binary operator here. But at least this interface allows us MDH developers to come up with a kind of quickly with a new kind of combined operator if it's requested from any kind of user here. And yeah, it's also already mentioned at the beginning of the talk, we can also take straightforward sequential code as input. So for example, Python code. And that's actually how a Python code would look like if you want to optimize it via MDH. So you just implement matrix vector multiplication via these typical 2 for loops. And then again, just use the decorator where you say, okay, what's my input data, what's my output data. You explicitly state the combined operators here. And that's actually everything you need to do. And that's completely equivalent, again, to the formal representation, also to the Python-based implementation that we have seen on the slides before. And yeah, and that's actually what the two other guys that actually could not join us here today are working on implementing. So they are trying to bring the MDH approach into the MLIR framework here. And regarding the high-level interface, their work is actually done, and they could come up with an interface that's, again, completely equivalent to the formal representation of MDH. So the formal representation, the Python representation, and the MLIR representation are completely equivalent. And here, for example, we can also see again, so we have these 3 higher order functions, infview, mdhom, outview. Index functions are, for example, expressed as affine maps, which are building blocks of MLIR. We have the type parameters and so on and so forth. And yeah, our MLIR interface has a particular advantage that allows easy integration of MDH into deep learning frameworks. So for example, what we are doing right now is, so from the MLR community, we already have a pipeline where we can lower TensorFlow and PyTorch programs to stable HLO. That's the kind of, so they call it the dialect in MLR that can be considered as a kind of IR. This stable HLO is lowered to linalg, that's the representation that we have seen like 3 or 4 slides before. So it's actually already provided by the MLR community. And from this representation, this linear representation, we can go now to the MDH representation and then generate the code according to MDH. So now regarding our low-level representation. So I have just one slide about the low-level representation so that you have at least seen it once. And the goal of our low-level representation is now to explicitly express in hardware and data optimized decomposition and recomposition of data per computations. So how can we make the problem gradually smaller, that it fits into the memory and core hierarchy of modern parallel architectures, and how can we recompose these computed intermediate results back to the final results? So that's what the representation tries to express formally here. And yeah, the second major goal is the representation. We have designed it that it can be straightforwardly transformed to executable program code. So for example, in OpenMP, CUDA, and OpenCL. And straightforwardly in this context means that all the major optimization decisions regarding data movement and parallelization are already explicitly expressed in this representation here. And here on the bottom left, you can see how such an instance in our low-level representation looks like. So nobody is expected to understand this, but What actually happening here, speaking very easy and very technically, is we apply a multi-layered, multi-dimensional tiling approach, and for each tile we say how it is assigned to the core hierarchy, how it's assigned to the memory hierarchy. So should tiles be computed in parallel, if in parallel on the GPU, for example, by blocks, warp, threads, and should these tiles be computed, for example, in register memory, shared memory, device memory, and so on and so forth. These kind of decisions are all expressed in this representation here. Okay, and we could also show, because of the design of our low-level representation, which tries to be very uniform and also try to follow some structure for all kinds of instances here, we could even visualize optimizations for different kinds of architectures and different kinds of computation in a uniform way, which is kind of this form. So here on the right side, for example, you can see here how the problem is made gradually smaller, in this case a matrix vector multiplication. At the bottom part, we compute on these smaller problems and then we recompose these smaller results to the final result. Now regarding our lowering process from a high-level instance to a low-level instance, so this is actually based on formally defined performance-critical parameters. And our parameters don't aim to introduce some kind of new fancy optimization here, but they aim to unify, generalize, and combine, and also formalize well-proven optimizations, particularly regarding tiling, data movement, and parallelization here. And what these parameters actually determine is, so they kind of influence the shape of our low-level instances here. And actually they say mostly, so how do we want to exploit the core hierarchy? How do we want to exploit the memory hierarchy, when speaking very easily? And yeah, maybe not very surprisingly, we determine optimized values of these parameters, so optimized for particular architecture and data characteristics using our ATF auto-tuning framework here. And yes, sure.
Yeah, I was wondering, since you brought up data movement, do you actually do prefetching of the data? Do you schedule data movement occupying the freedom, utilizing the bandwidth that might be available at a certain point in time or something like that? Or is it just how much data has to transfer from main memory to secondary storage or something like that? Yeah.
No, so this, these parameters actually really express data movement. So they say we want to make a data movement here. So in the formal representation, they just say we want to make a data movement. And it depends on the backend how this data movement looks like, the copy operation. But we just say, for example, this tile should be in this memory. How it gets there, it's dependent on the backend.
That can be instruction for the DMA engine or something
exactly,
like that.
Exactly, yeah, exactly. Okay, and as a side note, so if there's some expert or ninja programmer that says, okay, I know how to determine maybe, for example, some of these parameters, or maybe even most, we optionally also provide a scheduling-based language that where an expert can express some or maybe even all optimization decisions, for example, to reduce the auto-tuning time, or maybe because she or he thinks I can come up with better optimization decision than an auto-tuning system here. That's actually a paper that we had on CC, so if that's kind of interest for you, you can check out the paper here. So now regarding experimental results. So we tried to experimentally evaluate MDH in terms of all performance, portability, and also productivity. And for this, we tried to compare against the best available solutions to us right now, which are, for example, from the class of scheduling-based approaches, Apache TVM, which works for GPU and CPU. It's a very well-performing and decent competitor, and yeah, it actually was even recently acquired by NVIDIA here. Then we compared to two polyhedral compilers, PPCG for GPU, Pluto for CPU. From the class of functional approaches, we compared to the Lift approach, which works for GPU and CPU. And to make the experimenting really challenging for us, we also compared to domain-specific libraries provided by vendors, such as NVIDIA QBlast, CUDA for NVIDIA GPUs, and Intel OneMCL and OneDNN for CPUs. And these libraries are particularly challenging for us because they're highly optimized for a particular domain and for a particular architecture, while MDH and actually also other approaches that we compare to are more flexible in these kind of decisions here. And yeah, we have 5 different case studies also that we have considered, and these are linear algebra routines, particularly matrix multiplication and matrix vector multiplication. We have used stencil computations, Jacobi computation, which is the 1D stencil example, Gaussian convolution, which is a 2D example. Then a case study from the domain of quantum chemistry, coupled cluster. We have this data mining example, probabilistic record linkage, and also deep learning case study. And actually the deep learning case study is again the most challenging for us because most of the competitors are highly optimized for deep learning computations, particularly the vendor libraries and also TVM. So our performance evaluation. Our performance evaluation is based on a runtime comparison, and here I have just one slide where I just present the highlights only for deep learning because deep learning is the most challenging, or was the most challenging case study for us. And what you can see here is the speed up of our approach as compared to the competitors here. So higher is better for us, and you're not expected to read all these tables here. So I have the summary on the right side. And for example, on the GPU, compared to TVM, we have speedups ranging from 0.88 to more than 2x. Compared to the polynomial compilers, we have speedups sometimes by more than an order of magnitude. And even as compared to the hand-optimized libraries like QBLAS, CUDA, and N, we have sometimes speedups of more than 2.5x. And similar things apply to the CPU. So they actually, compared to TVM, we have sometimes speedup of more than 3x, and also compared to 1MCL, 1DNN, sometimes speedups even more than 9x here. And here keep in mind, so deep learning was actually even the most challenging study for us. And for other computations, like for example, just a straightforward dot product, as compared to TVM, we have a speed up of more than 170x, for example, most likely because dot products are not that much occurring in deep learning. The portability evaluation in our paper is based on the Pennycook matrix. So it might be not very obvious how to measure portability, but John Pennycook came up with this Pennycook matrix, which somehow can assess portability here. Without diving into too much detail, but a value close to 0 means low portability, a value close to 1 means high portability. And for the deep learning case study, for example, we could achieve speedups, we could achieve higher portability than TVM actually in all cases. And even actually also as compared to the other competitors here, which actually just achieves the lowest speed up of 0 only, mainly because they are bound to a particular architecture here, and thus they are not functional portable, and thus especially also not performance portable. And the product evaluation of our paper is based on intuitive argumentation actually, because classical code matrix like lines of code or development effort are not very meaningful for these short and concise programs as used by MDH and also the competitors here. Now regarding work in progress, results and future direction. So we think that's just a starting point, this MDH approach, and I think we have a lot of ideas for many interesting future directions that are kind of promising. So for example, particularly regarding expressing fusion-based optimization, so we think we can exploit algebraic information that are captured in our representation to express very aggressive fusion optimization on the high abstraction level and also the low abstraction level here. Then we have some ideas of how we can very structuredly target domain-specific hardware extension like tensor cores, for example, and also sparse computations, and actually many more. And that actually brings me to the summary about MDH. So I'll make it quick. So MDH's 3 key goals are to achieve performance, portability, and productivity in one combined approach. And for this, MDH formally introduces program representation on both the high level and also the low level. The goal of the high level was to express data per computations uniformly, fully agnostic of optimization and hardware details, while still capturing all the information that are relevant for generating high-performing code. And in contrast to the high-level representation, the goal was to now explicitly express and hardware and data optimize decomposition and recomposition of computations so that we can efficiently target the memory and core hierarchies of modern parallel architectures here. And MDH also introduced a lowering process so that the high-level instance in our high-level representation can be fully automatically lowered to a device and data-optimized instance in our low-level representation based on auto-tuning. And in our experiment, we could confirm that MDH often achieves higher performance, portability, and/or productivity than popular state-of-practice approaches, also including hand-optimized libraries provided by vendors. I think the most interesting point here is there are many interesting, promising future directions that we can hopefully present at some ARRAY event in the future. And just one last note about MDH. So that was of course a very quick informal dive and just regarding the high level representation of MDH. So if that could somehow gain your interest, we have a paper about that, the archive version particularly, which is a long version of the top-class version where you can find all formal details about all the stuff, the high-level representation, the low-level representation, the lowering process, and so on and so forth. And there are also a bunch of further experimental results provided. Okay, now kind of quickly regarding ATF. So again, regarding ATF, we have a website about that. So if that somehow can gain your interest, please feel free to check the website. And we consider the paper from TACO from 2021 as the main ATF paper here. So what is ATF? So ATF is first of all a framework or a tool that finds the values of performance critical parameters as we have seen for MDH, so like tile sizes, number of threads, but actually also these parameters can be arbitrarily complex. But actually a lot of approaches doing this, and the major goal or the major contribution of ATF is that it allows these kind of parameters to have so-called interdependencies between them by having the notion of constraints. So for example, that's particularly important when you target modern architectures like GPUs where you have hierarchies of memories and where you have different tile sizes on different layers. And of course the tile size on the lower layer needs to be chunked out of an upper layer tile, and that's something that you can express, for example, in ATF. And to efficiently handle these interdependencies among these kind of constraint parameters, ATF introduces novel processes to generating, storing, and exploring the spaces of these kind of parameters here. And that's actually based on two major contributions here. So ATF comes up with a new notion of constraints. So we define constraints on parameters rather than the search space. And we also introduce a new kind of search space representation that's particularly optimized for these kind of constraint parameters here. Maybe more interesting for us is how is ATF used and how can it be used here. So to use ATF, we have different kinds of interfaces, but I think the Python interface that Richard implemented and presented this year at the CC conference is the most interesting one. So to use ATF, you just implement a simple Python program. I would say it's simple. So because you just need to, so you just specify the parameters by their name, possible range, and constraints. The constraints can be any arbitrary lambda function here, for example, that may contain other kinds of tuning parameters here to express these interdependencies between parameters. Then you can implement your cost function, so the function whose cost needs to be minimized, for example, the runtime or the energy consumption, arbitrary in Python, so it can be any arbitrary Python function that takes a configuration as input and returns the cost. And we actually also provide pre-implemented cost functions for users' convenience. Yes, please?
How do we come up with these cost functions? Where do these cost functions come from?
So these cost functions are provided by the user because we don't know what kind of program you are tuning. You just need to specify a Python function where you kind of execute, which the function takes the configuration as input, so a particular choice of the parameters that you want to tune. And for this particular choice of parameters, you need to tell us what your program has a cost for example, by executing it and report the runtime to us. And that's how we use this function as a black box connection to your program, and that's how we optimize your program here. And then we say at the end, okay, this configuration led to the lowest cost. That's how it works.
So that means if you want to run your autotuner effectively, you have to essentially run bits of your code in different configurations on beforehand.
Either this or you come up with an analytical cost model or something like that. You just need to somehow tell us the cost of your program, and how you do that is up to you. So we actually run the program. So right now we don't have a cost model yet, but that's how we can keep this framework very generic. So that's also why it works for actually any kind of program. We just need to, that was the important point for us. Yes, please?
So for the benchmarks that I gave before, I assume you were using ATF.
Exactly, yeah.
And how did you use, what cost function did you use there?
That was, for example, for the GPU example, there was a CUDA cost function that we have implemented ourselves. So the kernel was kind of executed in this function, and then we have reported the cost to the runtime as cost there. So a Python function we really call a CUDA kernel that we have generated according to MDH, put the parameters in it so that the CUDA kernel was customized with the particular tile sizes, numbers of threads, and so on and so forth. And we have run it, measured the runtime of it using the CUDA API, and then reported the cost. And that's how we did the auto tuning there.
Thank you.
Okay, so yeah. And actually for CUDA and OpenCL, we also provide pre-implemented cost functions that you don't have to implement all this kind of host code where you issue the data transfers, need to compile the OpenCL or CUDA kernel, for example. And yeah, they're also kind of convenient to use. So in this example, for example, you can see even the pre-implemented CUDA cost function from us here. For example, you can see you just put the kernel code as a string into our cost function, and you say which GPU you want to target. In this case, the one with the device ID 0. What are your arguments? What is the grid dimension, the block dimension? That's everything you need to do for the cost function in this case here. And then we generate the host code for you and execute the kernel, measure the time, and so on and so forth. But you, for example, come up with a Java program, whatever, so you need to implement your own cost function. And yeah, ATF actually also provides various pre-implemented search techniques and abort conditions. So we have a bunch of different search techniques from numerical optimization. And we actually also have meta techniques, because meta techniques are, actually you have one meta technique that chooses automatically a search technique for you from our pre-implemented ones. So that's highly inspired by the OpenTuner framework from MIT here. And yeah, that's also kind of convenient to use there. And we also come up with a bunch of different abort conditions. So they tell when to stop the auto-tuning process. For example, based on the tuning time, based on the tuning results, or maybe as a compromise of both. So for example, you can say to ATF, okay, if within the last 2 hours you couldn't improve the result, just stop, and something like that. Okay. Yeah, that actually also already brings me to the summary about ATF here. So the major goal of ATF was to support parameters with interdependencies between them, and for this it has introduced novel process to generating, storing, and exploring the spaces of these parameters, because these interdependencies make things much more complex than in the easy case where you don't have interdependencies. But ATF actually has a bunch of further features that I could not present on the slides for brevity here. So for example, we put a lot of effort in providing a very productive user interface here, and in our papers we actually also argue that it's simpler to use than the interfaces of other approaches, even when you don't have interdependencies between your tuning parameters here. Then, as already mentioned, we have different kinds of search techniques and abort conditions, and the framework is actually extensible in both points here, so the user can also come up with its own search techniques and abort conditions. For this, for example, she or he just needs to implement a simple Python interface. And actually ATF provides different kinds of interfaces here. So the ATF concepts, we have implemented them in Python. That's what I've presented on the slide before, but we have also C++ interface. For example, when you want to auto-tune C++ programs at runtime. Then you have also domain-specific language, which is very easy to use, very convenient to use when you want to auto-tune just at compile time and not at runtime. And the ATF concepts actually could be integrated in any kind of general purpose language here. So also Java, if you want to auto-tune Java Java programs at runtime, and so on and so forth. But we don't have a Java interface yet. And yeah, that's actually the end of the talk. So thanks very much for attending and listening. And I think we should have plenty of time for questions now. Perfect. Thanks.
So this is the keyword, plenty of time for questions.
Yes, please.
Where are the questions? There.
So I'm wondering about the ATF side of things, and so I guess you're sort of saying that you sort of like black box optimization methods for a cost function. So then, so what sort of exploration, how do you explore the sort of search space? Like, is it that you have rewrites defined for the low-level MDH representation, or like what sort of approach do you use there?
So we represent the configuration, some kind of coordinate space, and then we have numerical optimization techniques to explore this coordinate space here, like for example hill climber, simulated annealing, and these kind of search techniques. That's how the exploration works.
Yes, but for instance, for simulated annealing, there's like some that you start from, you have some current configuration, and then you have the neighboring configurations. So
exactly.
what sort of neighboring configurations do you have? Like
okay,
which ones do you
I think your question goes more into the direction how the search space is represented, and that's kind of this structure here that you can see on the bottom right here. We have a tree-like representation of the search space here, and what we are doing, we are mapping this tree on a coordinate space, and the coordinate space actually, it has as many dimensions as you have layers in the tree, and then the values in the coordinate space are between 0 and 1, and then you say, that's how you can navigate through the tree. So for example, the first dimension of the coordinate space is mapped to the first layer in the tree, the second dimension, the coordinate space to the second layer, and that's how we kind of roughly map the coordinate space to the tree, and that reduces the challenge of exploring this tree to exploring a coordinate space, which actually is the most efficient structure for most of the search techniques that we have in numerical optimization.
Okay, so you also have like a generic representation of the search space.
Exactly.
Okay, yeah, and so that is also interesting to know. I did miss that, so that's my bad. But I do. And how do you construct the search space? Like, what sort of so you operate on the low level MDH representation at this point, right? Or something different?
So the MDH search space would be represented as such kind of a tree.
Yeah. Okay.
Is that what you meant? So if it's different kinds of parameters, each parameter is represented here as one layer in the tree. So when you have like 10 parameters, you have a 10-layer tree.
What sort of parameter could it be, for instance? Could you
a tile size, for example.
Okay.
A tile size, for example. Numbers of threads. Then exploiting fast memory resources yet or not. We have Boolean parameters also in it. So it's actually this. Where is it? This table here.
Oh, I see. Okay.
That's of course a very mathematical presentation, but these are, for example, these are numbers of so these are tile sizes here. For example, that's a loop. You can technically that's kind of a loop order. There's a permutation parameter. Then let's skip this one. But here's the memory regions. For example, tiles should be they computed in which memory region: global memory, register memory, shared memory when you target GPUs, and these kind of things.
So the lowering process itself.
It's generic in these parameters.
Okay,
so exactly.
Okay, that's interesting. Okay, thank you. Now that's a lot clearer. Thank you.
Okay, cool.
More questions?
I was wondering, in what sense do you use the word homomorphism? Is it there are a lot of operations that have a certain homomorphism?
That's actually a very good question, because I don't even have to bring the definition of homomorphisms here. So the function that we can express via our higher order functions, so with this kind of representation, need to be homomorphism. Homomorphism actually means that you can split the iteration space in any dimension, when speaking very technically, and then you have an operator, when you, for example, have split the iteration space, and you can compute independently on these two parts and then combine it together. In any multi-dimension means that any loop, for example, of the iteration space, in a more imperative setting speaking, can be split and you can combine the results here. That's these homomorphic properties here. When you have the input, you put it in two parts, compute on this part, and then you can combine it together, and the input can be split in any dimension of the iteration space here. That's actually what I meant. We have defined formally data parallelism. It's not on the slides here, but in the paper that's described what exactly the target class of computations for us, and all these computations can be expressed exactly with this kind of expression there at the top. Yes, Sven, please.
No, your phone.
Does it work now? Yeah. Yeah, thank you very much. Very exciting. This slide is actually perfect for my question.
Okay.
So I see lots of indices here, and I know that Python is not exactly very strongly typed. And how do you know that my arrays have sufficiently enough elements? And I assume that all your homomorphic transformations are fine, provided that I don't have out of array accesses.
So that's where we check that in the Python interface.
Well, generally, how do you make sure that you
have the iteration space sizes explicit? So we are setting in the iteration space size. We have this I and k. Then we can check via the index. I think so. What we actually do with these I and k are concrete values when we have, so they're statically known. And then we know based on the index functions how large these matrix and the vector, for example, must be, and then we just check that.
What if you don't know them statically?
Currently, you assume them statically. If you don't know them, so in our formalism, that would be some kind of undefined values. So it's not implemented yet. So in the implementation, they always need to be statically available, right?
And even if you do know them, how do you make sure that your matrices have enough elements? That actually the shapes of the matrices are matching your iteration spaces.
So for a fine index function, it's, I think, kind of easy. You just replace some kind of the lowest and the highest value and check if it's some kind in the middle there. And if you have not a fine index function, so the easiest way would be to just test all values there.
But there it just says M is buffer T. How do I know that M is of sufficient range?
So when you take...
Oh, you have down there your index M by IK, right?
Exactly.
And how do you know that the range, capital I, matches the dimensionality of M?
I'm not sure if I got the question, but I think Richard got it.
I think what you mean is when we actually run it, we pass NumPy arrays, and they have the shape inside of them, so we can check if the shape of the NumPy array matches the inferred size what Ari was talking about. So
if what we're getting, what we're expecting is kind of the same. So we can compute what we're expecting based on the static information that we have here. And what the user provides is kind of captured the NumPy array representation you meant. And then we can just check if that's...
Yeah, but can you check this statically?
I think so.
I mean, not statically, but at runtime of the Python program.
At the runtime of the Python program, but at the compile time...
So if it doesn't match, then you get an error.
Right.
But Python is sort of the meta language, right? It's just sort of setting up the program for execution and compiling it. So this
Exactly.
Is, like
Yeah.
Python isn't statically typed, but it's just the host language. Like it
Yes.
doesn't matter this, but it is doing the type on that sort of phase.
Yeah, but if you... Yeah, okay. Yeah, thank you.
Thank you, Richard.
Thank you. More questions? There's one more.
There's no other one because this is a technical detail. This is actually about the Python interface. I'm just wondering, the body of MTH-Matvec is the AST of that parsed? Are you literally executing that loop? Is there a point to executing it in that way, or is it that you're parsing the AST and looking at what the code is and then doing something else with it?
Parsing the AST.
Okay, it's a little sad, but I'll take it.
Anything else? Okay, so while you think about some other question, I have one myself. First of all, just a quick one. I assume auto-tuning is the key to your good performance compared to the other approaches. Is that fair to say?
Particularly compared to the vendor library, because the vendor library is only compared...
Of course, they can't do this. I mean,
exactly, so they are kind of optimized to what average high performance, particularly over data characteristic, and compared to them, I think our performance advantage is mainly because of the auto-tuning. I cannot tell you with certainty because the libraries are closed source, but most likely it's that. Compared to TVM and the other approaches might be different things because they're also involving auto-tuning, but particularly compared to QBLAS, QDNN, 1MKL, 1DNN, I highly assume that it's because of the auto-tuning, because we can specifically auto-tune also for the data shapes and sizes, while QBLAS and QDNN are just optimized for the architecture, but not specifically for the data sizes. I think they have kernels that are optimized towards a range of data sizes there.
One other question to the other side of your work. You call MDH a high-level representation, and I wonder what's the difference between a high-level representation and a programming language?
You can consider it as a programming language, but high-level representation means high-level in the MDH stack, kind of. So we have.
Yeah, I understand that, but the question is: so is that, or the excerpt of Python code that we see here, is that the way you expect things to be programmed?
Exactly. So maybe in the best case, in this way.
Mm-hmm. So it's basically a true.
Exactly. Yeah. So
One-to-one translation into Python. Yeah.
Exactly. Yeah.
Okay.
And the top part is a formal representation of that program there.
So you don't consider this to be, at least not at first, to be, let's say, a compilation target from something else, because that could be.
Of course, that could be. So we can.
But it's not your goal.
Not our goal, but being a backend for other approaches that operate on a higher level, of course, that would be very interesting for us. So we operate at this level, and yeah, that makes fully sense that it's a backend for other kind of approaches operating at higher levels there.
Okay. Then, while you still think about more questions, the last one from me. On slide 17, you had these buffers. At least that's what I noted down. Is this slide 17? Are there buffers? Yeah, there are buffers. So you expect that there are explicit buffers that you get in, or could these be kind of shared pointers in reality? Or do I have to copy everything into dedicated buffers before and copy it out after?
I think in this case we just say that these are just type hints, right?
Type hints here, but to your question, you can pass any NumPy array as inputs for these expressions, and of course these NumPy arrays can also be used in other computations. Is that what you mean with shared pointers? Or?
Yeah, I think so. Yeah, okay. Yeah. So it's not a dedicated buffer. It's just let's say a reference to a buffer that is somewhere.
Right. Yeah.
And the writing buffer,
But here in the decorator, these are type hints, right? That are not the actual buffers. The actual buffers are not in this code example.
Right. Technically, these are not type hints, but yeah, that are not the actual buffers. That are just the descriptions of the buffer type.
Oh, I see.
Okay, so not Python type hint, but the type information. So that's
Right.
what I meant. And the actual buffers are not in this example. So that's just the code that we need to generate the kernel. And this, for this generated kernel that we cannot see on the slide, there we put in the concrete buffers, right?
Right.
Right, then I use also the word right. And I don't see any other questions, so I would say let's thank Ari and Richard again.
Thank you.